All right, everybody, I want to give two videos on the ellipsoid method. So the ellipsoid method is the first polynomial time algorithm for solving a linear programming problem. In practice, it's very slow, but it had important implications in practice because it led to the interior point methods, which are both polynomial time and fast when you implement them. So here on the right, this egg-shaped picture is an ellipsoid. We all know an ellipse in 2D. You can also have ellipsoids in 3D or 4D or 5D. They're just affine transformations of a ball in that dimension. So the optimization problem we're going to solve is actually just finding a feasible solution. One of the recurring themes of this class is that finding an optimal solution is in some sense no harder than just finding any feasible solution. Our first explanation for that was this binary argument where you sort of keep reducing the size of the feasible solution to get better and better solutions. Our second argument for this was really just the simplex method. Phase one of the simplex method is finding any basic feasible solution. And that's no easier or harder than the simplex method to find an optimal solution. And then our third argument for why finding an optimal solution was really no different than just finding a feasible solution was the duality of linear programming. So this gray box here is copy and pasted from an earlier video. But let's say we wanted to optimize this primary problem, okay, you can sort of add in some of the material from the dual programming problem as constraints. So our dual programming problem has these constraints, so let's add those in. Weak duality says that any solution X for the primal problem is always has an optimum that's bounded from above by an optimum for the dual. So this is what weak duality says, okay? So any solution X to the primal and any solution Y to the dual always satisfy that the optimum for the primal is bounded from above by the optimal for the dual. So if we reverse that inequality and put this in, now any feasible solution to this program, has the property that it optimizes the primal. So in any case, that's what we're going to do with the ellipse method. We're just going to find any feasible solution. Questions so far? All right. We're trying to find any feasible solution. Let me give an analogy. So pretend you have this Sahara Desert and you're trying to find a lion in the Sahara Desert. One way you might search for this lion is you might divide your desert in half, and then you rule out that your lion can't be on the right side. So you search the right half of the desert. And then you do a similar division where you divide the remaining part of the desert in half, and maybe you rule out that the lion's not here. And then you keep going. You rule out that the lion's not on this part. You rule out that the lion's not on this part. And you keep going, and you get better and better information about where the lion might be if the lion indeed actually is in the desert. Okay. The difficulty with this approach, as I've outlined, is you're going to keep going forever, right? You're going to keep subdividing the desert and getting better and better constraints on where the lion might be, if the lion exists, but you'll never be able to say, aha, I found a lion and a lion is, right here. Or you'll never be able to say, aha, I've proven that there's no lion, just because all that we're doing is we're saying if a line exists, it's in this smaller and smaller region as we go. So what we're instead going to do is we're instead going to set things up So we're going to pretend our line has size at least epsilon. Okay, so our line is a pretty big line. And then when we start doing these steps, you know, we rule out that the line's on the right half, we rule out that the line's in this bottom region. Eventually we'll be able to end, because either we'll, you know, we'll find a point in this epsilon ball, you know, and we'll say, aha, we found the line, or pretend the line doesn't exist. We'll keep going and keep subdividing, and we'll get down to a region whose volume is too small to even contain said line. Okay, so if the only remaining area where the line could be is smaller than the volume of a line, then we can say with certainty that there's no line in this desert. Okay, let me try to make this analogy more precise. We're not searching for a line, we're searching for a feasible solution. Okay, so in our notes today, P is going to be the feasible region. It's going to be this convex body. So P is the set of all points X such that AX is at most B. And we're trying to find some X in P, or we're trying to prove that P is the empty set. All right. So roughly speaking, what we're going to do is our algorithm is going to rule out regions and say like, aha, no point in P is in this purple region. And then no point in P is in this purple region. And then no point in P is in this purple region, etc. Okay. And the problem is that if we set things up as I've described so far, you know, we can keep constraining the size of P, but pretend P were the empty set, right? How do we know when to stop? Right? Like no matter how small I constrain the size of P, P could still be, you know, smaller and still exist. I just, my eyesight's not good enough to see P or not. So we're going to recast things so that in some sense, P has, you know, a certain amount of volume, right? Like we're going to do this epsilon ball idea. So how do I want to explain this? Okay, so here's P. And I sort of outlined for you how you can try to rule out area and get down to a point in P. We're actually going to expand P a little bit. So here is going to be P plus epsilon on all sides. Okay, and now the point is that you know, P plus epsilon on all sides, it has at least a certain amount of volume in terms of epsilon. So now if I constrain the region where P could be smaller and smaller and smaller, and I get a region that has too small a volume, smaller than that of an epsilon ball, then I know P is the empty set. The ellipsoid method is polynomial in terms of the input size. The input size is the bit size of our matrix and the bit size of our vector B. And so we're going to choose epsilon carefully in terms of the bit size. So the bit size depends on how large the entries in our matrix are. So if our matrix has really large entries, like 1,000,003,000 is one of our entries, the bit size is going to be really large, this bit size phi. And so epsilon is therefore going to be really small. And what's cool is that you can prove that AX at most B has a solution. So in other words, P has a solution, if and only if this weakened inequality, all right, so this weakened inequality, maybe I should write, in some sense, this is P plus eta on all sides. In this weakened inequality, I've made the constraints easier to satisfy, okay? And the polytope that we care about has a solution if and only if this expanded polytope has a solution. And furthermore, when this expanded polytope has a solution, it has a solution that's large. It has a ball's worth of solutions. So when this expanded polytope has a solution, it has an entire ball's worth of solutions.
I think the bottom part of the page might be off the screen for us.
Oh, you can't see epsilon ball?
Oh, I thought there was something in the gray highlighted below.
Oh, okay. Yeah, there will be, but
oh, never mind then.
So in any case, this is the solution that the ellipsoid method is going to solve. We're going to expand our polytope a little bit, and then we're going to find whether or not there's a solution. And we're going to leverage the fact that if there's a solution, there's indeed a full epsilon balls worth of solutions. All right. We're always going to start by searching in some large ball, and we're just going to assume that our polytope is contained inside this large ball. The gray box is sort of explaining why that's a good assumption, but let me not say anything about that for now. So here's the actual ellipsoid algorithm. Your inputs are a matrix A, a vector B, rational numbers R and epsilon. And we're assuming that our feasible region, if it's, it might be empty, right? But we're assuming that our feasible region is contained in this large ball. So our feasible region is contained in the super large ball. And then we're trying to solve a problem where if our feasible region contains an epsilon ball, then we return any point in our feasible region. And if not, we'll either return no solution or we'll return a point in our feasible region. So we're trying to decide, if this polytope has an epsilon ball inside it or not. We apply this algorithm on these inputs, okay? So our feasible region is actually this expanded polytope. And it turns out that when you set up the inputs correctly, if you have a solution, then you have a full epsilon ball, okay, when you set up the inputs correctly. So if you have a solution, you're actually going to be in this situation where you have a full epsilon ball. So when the inputs are set up as prescribed above, you're never in the case where you don't have an epsilon ball, but you return a point. Okay. But for other inputs, you might not have an epsilon ball, but you do have some point. Okay. So to end this video, let me briefly say what we're trying to do. We start with actually an ellipse that contains our feasible region, and we're trying to decide if our feasible region has an epsilon ball inside it or not. roughly speaking, we're going to get a sequence of smaller and smaller ellipses, which always contain the feasible region. And we keep getting down and further to smaller and smaller ellipses. Okay. And we'll keep going so that either we say, aha, our feasible region is contained in this ellipse that has a very small volume, so our feasible region can't contain an epsilon ball, or we'll find some center point of the ellipse, which is inside the feasible region, and therefore we'll have found a solution. And I'll give you the details of that in the next video. Any questions?
Yeah, I have a quick question. So, you know, we put in this rational number R for the basically our search volume.
Yeah.
How do we know that's big enough that it actually, because you can imagine P is outside of that search area.
Thanks so much, Patrick. I swear I didn't feed Patrick that question, but it's really helpful because this is what's in that gray box. And I was getting a little too far into the weeds, so I didn't want to go into the gray box. But okay, so we're trying to decide if there's a feasible solution to this, AX at most B. And I already described how, in terms of the input size, right, the size of the entries of our matrix in our vector, you can choose this eta and epsilon so that AX at most B has a solution if and only if the slightly weaker linear program has a solution. And when it does, it has an epsilon ball. There's a similar fact, Patrick, that allows us to get this bounding ball R of radius R that contains our feasible region. So it turns out that AX at most B has a solution if and only if the stronger problem with more constraints has a solution. And so phi is the input size of our problem. It turns out every variable has to be between, 2 to that large power and the negative thereof. All right. So you can prove my matrix has, say, entries up to 1 million, and this vector B has entries up to 1 million, right? And you can prove that any solution has entries in absolute value that are bounded above by 2 to the 1,000,000th power, right? So your solution can't have values on the order of 2 to 1 million if your input problem only had entries on the order of size 1 million. And so really this is finding a constraining cube, right? We've taken our polytope and we've founded some, much larger cube that contains it, right? And then you just find a ball around that cube. And so you know that if your solution's in this cube, it's also in the larger ball. Good question. Other questions? Thanks, everybody.